Hello students, myself Dinesh Prabhakar. Welcome to Process Control lecture series. In my previous lecture, I discussed about the PD control mode and PID control mode. That means in that lecture, I complete composite control mode. So we discussed all the type of the controller mode. That means first we discussed the derivative composite control mode like the PI, PD and PID control mode, and we also discussed the individual modes like the PD and the proportional plus derivative and integral control. Now in this lecture we discussed about the analog controller, and in this lecture we discussed the two position controller and proportional mode and integral mode. So now we start the another type of controller. This is known as the analog controller, and this is also same as the PID controller. That means in the analog controller we also learn the position controller, proportional controller, integral controller, derivative controller, and we also learned the composite mode, that means the PI, PD and PID, but in the form of analog controller. So now we start the analog controller. An analog controller is a device that implements the controller modes described previously using analog signal to represent the loop parameter. That means simple definition of analog controller is nothing but a controller that use analog signal. So the analog signal used to control the device. The analog signal may be in the form of an electrical current or in the pneumatic air pressure. So the analog signal that give to control the device is in the form of either electrical current or in the form of pneumatic air pressure. Now we discuss about the two position controller. That means in the analog controller we start learning of first controller, and that is the two position controller. So here this is the diagram of two position controller of analog controller. So here you can see we use the op-amp and the comparator to build this diagram. A method using op-amp implementation of on-off controller with adjustable neutral zone is given in this figure. For this circuit, we assume that if the controller input voltage V reach a value Vh, then the comparator output should go to the on state, which is defined as some voltage V0. So here we assume first one, that means the controller input voltage V, that means input voltage we have given V reach and the value of the Vh, that is the higher value, then the comparator output, we can see the comparator output should go on the end state, which is defined as the V0. And when, on the other hand, when the voltage fall below the value Vn, the comparator output should switch to off state, which is defined as 0 volt. So this is the on-off, or we can say as a two-position controller. The operation is same we discussed previously. That means here two mode. First one is the on and second one is the off. So here the input voltage when it goes to the Vh value, that means a higher value, at that time the controller is the comparator is on and is give the output voltage V0. And when the controller fall below the value VL, the comparator output should switch the off state, which is defined as the 0 volt. Now, the comparator output switch state when the voltage on its input V1 is equal to the set point value VSP. Analysis of this circuit shows that the high, that means on switch voltage is VH is equals to VSP. That means when the VH is equals to VSP, at that time the controller is on state. And the other end, the low, that is the off switch voltage is given by VL is equals to VSP minus R1 upon R2 into V0. You can see the resistor value R1 and R2. So by using that, we get the low voltage, that is the VL is equal to VSP minus R1 by R2 into V0. This indicates the low voltage. Figure show the typical two-position relationship between input and output voltage for this circuit. The width of the neutral zone between the VL and VH can be adjusted by variation of R2. That means we can adjust this neutral zone. That means the width between the VL and VH can be adjusted by varying the value of resistor R2. The relative location of the neutral zone is calculated from the difference between equation number 1 and 2 that we have discussed already in the previous slide. Now we discuss about the proportional mode, that is proportional controller of the analog controller. So this is the figure of proportional controller. The electrical expression for this mode is given by P is equals to Kp EP plus P. This is the same as we discussed in the proportional mode lecture. That means this is the proportional mode analytical equation. And here this Kp is indicating the proportional gain between the error and controller output. Same as this P0 is indicating the controller output with no error. That means when the error is 0, at that time the controller output is indicated by the P0, or we can say as the initial value. And the EP is indicating the error in percentage of variable range. Now if we consider both the controller output and the error to be expressed in the terms of voltage, we see that the equation 1 is simply a summing amplifier. That means the open circuit in the figure shows such an electronic proportional controller. In this case, the analog electronic equation for the output voltage is given by Vout is equals to Gp Ve plus V0. So here the Vout is indicate the output voltage, Gp is indicate the ratio of resistor R2 by R1, and we can say this is the gain of this controller. And this V indicate the error voltage. So this is the equation for the analog proportional mode controller. And V0 indicate the output with the 0 error. The design of the proportional controller calls for the specification of the proportional gain described by K Kp in equation number 1 that express the percent of output for an error of 1% of the measurement range. Alternative, it could be described as the proportional band as Pp is equals to 100 upon Kp. So this is the equation for the proportional band. This is the relation between the Pp, that means the proportional band, and Kp, that means Kp is the proportional gain. So we can write the Pb is equals to 100 upon Kp. This must now be expressed in terms of the voltage gain Gp in equation number 2. The relation between Gp and K is given by Gp is equals to Kp delta V out upon delta V in. And here this delta V out indicates the range of output voltage. Delta V in indicates the range of measurement voltage. So this is the relation between the Gp and K, and is given by Gp is equals to Kp delta V out upon V in. Now we discuss about the second one type of controller mode, that is integral control mode. So here you can see this is the figure of integral control mode, that means analog integral control mode. The analytical expression for the integral mode is given by the equation as Pt is equals to Ki 0 to t Ep dt plus P0. We know this is the analytical equation for the integral mode. And here we know this P0 indicates the controller output when the integral action starts. That is the initial value of the controller output. And the Ki is the integral gain indicate, and the Ep is the indicate the error. This function is easy to implement when op-amp are used as a building block. A diagram of an integral controller is shown in this figure. The corresponding equation relating input and output is given by V out is equals to Gi 0 to t V0 dt V0. So V out 0. So here V out indicates the output voltage. Gi is equals to 1 upon Rc, and it's known as the integration gain. And this VE indicates the error voltage, and the V out 0 is indicate the initial output voltage. So this is the this is the equation for the integral mode. The value of R and C can be adjusted to obtain the desired integration time. That means we can get the desired value of this integration time by varying the value of the resistor and this capacitor in this figure. The initial controller output is integrator output at t is equals to 0. As we noted earlier, the integration time constant determines the rate at which the controller output increase when the error is constant. That means we can see here, as we noted earlier, the integration time constant determines the rate at which the controller output increase when the error is constant. If Ki is made too large, the output rises so fast that overshoot of the optimum setting occurs and cycling is produced. That means oscillation is produced when the Ki value, that means the integration gain, will increase, or the value of the Ki is large, then the output rises so fast that overshoot of the optimum setting occurs and cycling is produced. So in this lecture, we discuss about the analog controller, and in analog controller, first we discuss about the two-position controller, then we discuss about the proportional controller, and last we discuss about the integral controller. Thank you.